Good evening once again, and welcome to another episode of the BJ's Physics Classroom. In this section of the Physics Classroom, we are going to continue with um, electrostatics. If you remember, the last time we met in our previous section, we looked at resultant forces and how to answer questions on resultant forces. Then we came to electric field, then we dealt with electric field intensity. And we saw that electric field intensity is defined as the force per unit charge placed at a point in an electric field. The force per unit charge placed at a point in an electric field. So we saw that electric field intensity, the symbol is E. We saw that E is equal to force per unit charge placed at a point in an electric field. And we said the unit is Newton per Coulomb. When we put the value of F here, another formula for electric field intensity will give us K over D squared. This is the charge that is experiencing the field, and this is the charge that has created a field. So when you calculate for a field intensity using the charge experiencing the field, then you have to use this formula. If you are calculating for electric field intensity using the charge that has created the field, then you have to use this formula. So we have equation 1 and equation 2. Take note of these equations very well. Good. Let's look at resultant field intensity. Resultant field intensity. Let's take, for instance, we have two charges Q1 and Q2, that are placed at a distance d apart from their centers, all right? We can be asked to find the resultant field intensity at any point between these two. Let us consider the resultant field intensity at the point P, such that if the distance from here to here is x, remember, the whole of this is d, right? Then the distance from here to here becomes d minus x. I hope that is clear. The distance from here to here becomes d minus x. So all that we have to do is we have to do just like we looked at under resultant forces. Just like we looked at under resultant forces. We take into consideration the charges of these two bodies. So what you do is that you can place any charge here. You know, there are so many ways of doing this. One of them is what I'm going to talk about exactly. So place, let's suppose that this charge is positive and this charge is negative. So we place any charge here. Whether you place a positive charge or a negative charge here, your answer is still going to be the same, exactly. So just place a test charge here. Let's suppose that we place a positive test charge. Because this is positive and this is positive, it means that this charge is going to repel this one away. So this charge will move away. So the field intensity due to this charge at this point will point in this direction. Let's call it E1. The field intensity due to this one, this is positive and this is negative. So there will be attraction. So this one will be pointing towards this direction. So E2 will be in this direction. Since the two resultant fields are in opposite directions, are in the same direction, the two fields are in the same direction, we add them. So the resultant field intensity E is equal to E1 plus E2. That is how we find the resultant field intensity on a charge. The resultant field intensity on a charge. When the two charges are in opposite directions, what you do is that when the two fields are in opposite directions, what you do is that you subtract them. You subtract the smaller field from the bigger field. Exactly. Just like we looked at under resultant forces. You can also use the direction of the field, the direction of the electric lines of force. All right. For instance, if I'm using the direction of the electric lines of force, for instance, I have a charge Q which is positive, I have a charge Q which is negative. So if I'm using the direction of the resultant force, the direction of the electric lines of force, the electric lines of force due to this charge will move away from it, right? Good. The electric lines of force due to this charge will move towards it. So E1 is pointing here, E2 is pointing here. The two of them are pointing the same direction. So E is equal to E1 plus E2. You understand? So that is also another very easy method. But because I used the attraction and the repulsion method for the resultant forces, I just want to create continuity in that so that you will always be able to handle it. Good. So that is what we mean by resultant field intensity or a charge. So we look at another term we call electric potential energy. Electric potential energy. When we say electric potential energy, we define it as the work done per unit charge. Sorry. We define electric potential energy as the work done in moving the charge from infinity to a point in an electric field. The work done in moving a charge from infinity to a point in an electric field. Let me explain this using a diagram. Let's suppose that we have a charge Q that has created a field. We want to move a charge outside this field. You know, any charge which is outside the field is at infinity, right? We want to move this charge from this point to this point such that it will be of a distance d from this point. So the work done in moving this charge from infinity to this point in the electric field is what we call the electric potential energy. All right? And the electric potential energy is given by negative K, capital Q, small q, all over d, where d is the distance between the two charges from where it is in the field to the charge that has created the field. Good. That is electric potential energy. All right? Now look at this. You know, the potential energy we know already is directly proportional to height. But as you can see, the potential energy here is inversely proportional to the height. So in order to make the potential energy directly proportional to the height, the negative. So the negative sign makes the potential energy becomes proportional to the height. You understand that? So that as the height increases, the magnitude, remember that potential energy is a scalar quantity. So the magnitude of the potential energy increase. The magnitude. We are not talking about, it doesn't have a direction, all right? So it is only to make the magnitude, the value, become bigger. Exactly. Good. Good. So that is electric potential energy. Then we look at another term that we call electric potential. Electric potential. The symbol for electric potential is E. Remember that the unit for electric potential energy is joules, right? The unit for electric potential energy is joules. The symbol for electric potential is V. Sorry. The symbol for electric potential is V. The unit for electric potential energy is joules. Good. So when we say electric potential, it is defined as the work done per unit charge. The work done per unit charge in moving that charge from infinity to a point in an electric field. You know, the difference between the electric potential energy and the electric potential is that the electric potential energy is just the work done. But the electric potential difference is the work done per unit charge in bringing that charge from infinity to a point in an electric field, all right? The work done per unit charge in bringing this charge from infinity into this point is what we call the electric potential. So we say that V is the potential energy, the work done per unit charge in moving that charge from infinity to a point in an electric field. All right? Let's call this equation 1, we call this equation 2. But when we pick this value and we put it here, that will give us V is equal to K, capital Q, small q, all over D times small q, negative. Remember, the value for this is negative. That will make this one cancel this one. Then we get V is equal to minus K, Q all over D. This is the relation for finding electric potential. The unit for electric potential is volts, unit. Volts. We shorten it as V, right? That's the unit for electric potential, volts. Good. Then we look at another term we call electric potential difference. When we say electric potential difference, now the charge is in the field. All right? Let's consider a charge in the field. We want to move this charge in the field at a point of low potential to a point of high potential in the electric field. We are no longer moving it from infinity to the field. We are moving it from one point in the field to another point in the field, from a point of low potential to a point of high potential in the field. That is what we call electric potential difference. I hope you understand what I'm talking about. Good. So electric potential difference is the work done per unit charge in bringing that charge from a point of low potential to a point of high potential in an electric field. All right? So let us suppose that, so we are talking about electric potential difference. Electric potential difference. Let us consider an electric field created by a charge capital Q. There is a charge at this point. There is a charge at this point, P. We want to move this charge. Let the potential here be V1, right? We want to move this charge from this point to this point. Let the potential here be V2. You understand that? The potential here between this one and this is V1. The potential between this one and this is V2. Or the potential at this point is V1. The potential at this point is V2. We want to move this charge from a point of low potential to a point of high potential. So the electric potential difference, delta V, is given by V2 minus V1, where V1 is of low potential and V2 is of high potential. All right? Good. This is how we find the electric potential difference. But we know that the value for V is like this. So therefore, I'm going to get delta V is equal to, when I put this one in, that is going to give me negative K Q over D2. Let the distance here be D2. Let the distance here be D1. Minus into bracket minus KQ over D1. So the same values at the top here. This minus will make this one plus. So we factorize KQ out. That will give me delta V is equal to KQ into bracket. Now look at this. This is going to make this one positive, but this is already negative. So that will give me 1 over D1 minus 1 over D2. All right? This is the summary of the formula which is used to find the electric potential difference at a point in an electric field, which we define as the work done per unit charge in moving that charge from a point of low potential to a point of high potential in an electric field. Good. So we look at another term we call equipotential surface. We call it equipotential surface. Equipotential surface. Now, equipotential surface refer to points of equal potential in an electric field. So when you pick an electric field, there are points within the electric field where the electric potentials are the same. These points are what we refer to as equipotential surface. Good. So when we say equipotential surface, for instance, in an electric field, let's take it that all these points that are represented by dots are of equal potential, right? The potential here to this point is the same as the potential here to this point. If it is the same throughout, then these points form a surface. That surface is what we call equipotential surface. Good. Then, so when we sketch a graph of electric potential or graph of electric field intensity versus displacement or distance versus distance. For a point charge, we are looking at the graphical relationship between electric field intensity or electric potential of an electric field versus distance or displacement, all right? So for a point charge, a point charge is like this. So if we sketch the graph of either field intensity or potential, the two of them are the same, exactly. The two graphs have the same characteristics. Versus distance. So this is positive distance, this is negative displacement, this is positive displacement. As you move away from the charge, the electric field intensity decreases with distance. As you move away from the charge, the electric field intensity decreases with distance, right? The same way, the electric potential also decreases with distance. Why? Because the field intensity is given by Q over D squared. So it is inversely proportional to the D. And the potential V is also equal to Q over D. KQ over D, right? Good. So when you sketch the graph of field intensity or electric potential, the two of them will give you the same thing like this for a point charge. Then for a charged sphere, B, for a charged sphere, let's suppose that, let's take this to be the sphere, right? When we sketch a graph of field intensity or electric potential versus distance, negative displacement, positive displacement versus distance, the graph behaves like this. It doesn't really have a specific place that it must start from the top here. But what happens is that there is, this is the radius. This is the radius of the sphere, right? Because of electrostatic equilibrium, the resultant field intensity inside a sphere, a charged sphere, is zero because of electrostatic equilibrium, which I have explained earlier in other videos. Is it the first or the second electrostatic video? Yes, I explained electrostatic equilibrium. Good. So what happens is that, so because of that, the resultant field intensity is zero. So the field intensity starts from the surface of the charge, because for a charged body, the charges are on the surface for a charged sphere or body, the charges are on the surface of the sphere. You understand? So the field intensity begin from the surface of the sphere and then they move out like that. So the distance, the field intensity decrease, the electric potential also decrease, the field intensity decrease, the electric potential also decrease with respect to distance. Is that clear? Good. Good. So that is the graphical representation of electric field intensity or electric potential versus displacement. Take note that the resultant field intensity here is 0. E is equal to 0. All right? That is within the charged sphere. The E is equal to 0. Good. Now, let me play around the equations more so that I can obtain another relation between electric field intensity and the electric potential. Look at this. We know for purpose of what I'm going to do, let us ignore the negative sign for the electric potential. So we say V is equal to K Q over D. Let me call this equation 1. For electric potential, it's supposed to be negative, but I'm ignoring the negative. Good. And then V is equal to KQ over D squared. Let me call this equation 2. Sorry, this is electric field intensity. Let me call this equation 2. So what I'm going to do is that I'm going to multiply through this equation 2 by 1 over D, right? Sorry, I'm going to multiply through equation 1 by 1 over D. So multiplying equation 1 by 1 over D, that is going to give me V over D is equal to Q over D squared. Equation 3. Now when we compare equation 3 with equation 4, with equation 2, when we compare equation 3 with equation 2, we can see that the electric field intensity E is equal to V over D, which is easier kept in our head as V is equal to ED. You know, I find it easy to keep it in my head like this than to keep it like this. You understand that? So we say that V is equal to ED. This is another relation that exists between electric field intensity and the electric potential. So we say the electric potential is given by V E times D, where E is the electric field intensity and D is the distance. So because of this formula, another unit for electric field intensity is volt per meter. So if you meet a question somewhere and they give the unit volt per meter or Newton per coulomb, which is the former one that we have seen from the definition, the two of them are correct for electric field intensity. Good. So let's look at charge between parallel plates. Charge between parallel plates. Let me state that it is based on this principle, that Millikan was able to do his charge quantization principle. Exactly. He was able to calculate for the quantity of charge using this principle that I'm going to do. Resultant force, charge between two plates, and the resultant force on charge. So here we look at resultant force on charge between two plates. All right, good. So let us first consider two plates. The down plate is F. The down plate is F, like this. The top plate is connected to a very high potential V. Let's suppose that we place a positively charged body here. Because the top plate is positively charged, you know the voltage is positive, so the top plate is positively charged, and this one too is positive. It means that the electrostatic force between this one and the charge will be downwards because there will be repulsion. So the electrostatic force will be downwards like this. And the weight of the charge will also be downwards like this. So therefore, the resultant force on this charged body is going to be given by R. Let R be the resultant force. R is equal to F plus W, because the two forces are in the same direction. Because the two forces are in the same direction, we add them. All right. What about if we have a situation like this. This charge is negative. The down plate is earthed. You know, the earthing of the down plate leaves the down plate's no potential. Anybody which is earthed has zero electric potential, right? So the electric potential here is zero. The electric potential is maximum. What that means is that the potential difference between the two plates is the potential here, right? That's why we earth this one. The electric potential between the two plates is the potential here. That's why we earth this one. Good. So because this is positive, the charge, the plate is positive and the charge is negative, there will be electrostatic force which will be acting upward like this. And there is the weight which is acting downward like this. So the resultant force R is given by W minus F, where W is bigger than F, all right? So we subtract the smaller force from the bigger force to get the resultant force on the charge. The resultant force will determine where this body is supposed to move. If the F is bigger than the W, the charge will move up. If the W is bigger than the F, the charge will move down. Do you understand? Good. So this is how we find the resultant force on the charge. Now look at this. How do we determine the F? As for the W, the weight W is equal to the mass times gravity, acceleration due to gravity. So no problem with that. Now the problem is with this. The problem is with the F. How do we determine the F? That is when this principle I earlier talked about comes in. How do we determine the value of F? The force F between the, you know that electric field intensity E is equal to F over Q. Let's call this one equation 1. That is F, this F is the electrostatic force, F. All right? The electrostatic force, F. But we also know that V is equal to, E is equal to V over D. You know, we just saw this equation. E is equal to V over D. That is equation 2. Where D is the distance between the two plates. D is the distance between the two plates. And V is the potential difference between the two plates. But the potential here is 0, the potential here is 0. So the potential difference is just the voltage across the upper plate. Good. So when we combine these two equations, we can see that F over Q is equal to V over D. So therefore, the electrostatic force F is equal to VQ over D. This is how we determine this quantity F. This is how we determine this quantity F, so that we can then put it inside this equation to determine the resultant force on a charge placed in an electric field. Thank you very much for being part of the BJ's Physics classroom today. This brings us to the concept of electrostatics, but we are not done. We still have capacitors to deal with, right? So in our next episode, we will begin with capacitors. Capacitors is you know, basically a device whose operation is based on the applications of electrostatics, exactly. So it's more or less an application of electrostatics that we are going to do under capacitors. So in our next video, we will look at capacitors. Maybe 2 videos and then we'll be done with capacitors, exactly. Thank you very much for subscribing to my YouTube channel. If you haven't done that, please just click on the subscribe at the top corner. See where I'm pointing? Click on that. It will subscribe you to my channel so that anytime I post a video, you will receive a notification. To my left too, you have some videos that I have done already on electrostatics. When you click on that, it will lead you to my YouTube channel, which is BJ Online, and then you can access all the videos that I have done. Thank you very much. Till I see you again, it's your man BJ. Stay blessed.